Hi everyone. Welcome to a lecture covering another degradation mechanism, creep. Like fatigue, it's caused by a gradual accumulation of damage until failure. Also like fatigue, this happens well below the yield strength and manifests as inelastic behavior. If we recall the standard route to inelasticity, if the load in the material exceeds the yield strength, then it commences to plastically deform. This deformation is permanent and will not be recovered once the load is removed. Creep deformation occurs that when a load is applied, it will elastically deform, and then if some stress is maintained, it will inelastically deform permanently and then unload elastically if the load is removed. This accumulated creep strain has the same characteristics as plastic strain, but it occurs by a very different mechanism. This creep deformation only needs a load and time to occur. However, temperature really speeds this up, and it can even occur at room temperature. You'll have to take my word for it, but both of these wires are made of the same material and are loaded well below their yield strength. One is significantly longer. The end of it is roughly out of frame. As you can see, the long one fails or ruptures before the short one, but they both elongated significantly before failure. This elongation was creep strain, and it occurred at room temperature. You might have also observed that the rate of deformation, that is, how fast the weights are moving, seems to accelerate as the wires finally rupture. Attempting to show creep strain on a stress versus strain plot doesn't really demonstrate the effect of time. Creep effects are typically communicated with the rate of creep strain accumulated as a result of time. For temperatures that are below a particular point, then creep doesn't really do that much. At temperatures below 40% of the melting temperature of the overall metal, then there really isn't any creep strain that accumulates, at least perceptibly, over extremely long periods of time. Polymers also have this threshold temperature of 40% of their melting temperature, and for ceramics it can be up to 60%. Creep curves have characteristics that all look the same, but the conditions that escalate the creep rate, that is, the change in the creep strain with time, is either an increase in the static load for a given temperature or an elevated temperature for a given load. When the temperature is above 40% of the melting point of a material, a characteristic curve looks like this, where there is first an instantaneous deformation, which then leads to primary creep, where the rate increases fairly rapidly until hitting a steady increase in the secondary region. The secondary region is where the slowest rate of creep accumulation occurs, and this is where materials that are subjected to creep conditions reside. After this, tertiary creep starts to take place and the rate increases again to rupture. Titanium, nickel, and steels and their alloys are used in high temperature applications. It can clearly be seen why. Their melting points are very high. However, lead and tin's melting points are quite low. Tin melts at approximately 200 degrees Celsius, meaning that alloys featuring these lower melting point metals are in the creep regime at room temperature. That explains why creep was demonstrated in the two wires shown previously, but it doesn't explain why there was a size effect observed. The longer wire ruptured before the short wire. I'll get into why in a minute, but for a representative creep test, we can come up with an empirical relationship which describes the minimum creep rate. Like we have seen previously regarding other elevated temperature phenomena such as diffusion, the creep rate is captured with an expression that looks like this. Here, Q, K, and N are coefficients which describe the material system. Both higher temperatures and stresses will exponentially increase the creep rate. Let's see how with a genuine material system that is employed for conditions that nominally see very high temperatures. Here are realistic creep curves for MAR M247, a nickel-based superalloy that's employed in stationary gas turbines. 870 degrees Celsius the creep behavior is observed to change dramatically. There is a 5-fold decrease in the amount of time required to rupture the component if the load is doubled. The other point of observation is there does not need to be very much strain before rupture, only 2%. Let's look at why. These micrographs are from the same alloy, prior to and after creep testing. The microstructural features are not important, but the overall morphology of the microstructure is on a qualitative basis. There's not much difference in how the microstructure appears between the starting material and even that exposed to 870 degrees Celsius for 1,000 hours. However, a difference by a few hundred degrees results in gross changes in the microstructure. This is a phenomenon which pertains to nickel-based superalloys. At high enough temperatures, diffusion allows the material to start rafting, or developing a texture aligned with the loading direction. It's not surprising that the microstructure doesn't change significantly at 870 degrees Celsius for 1,000 hours. This is actually the least aggressive creep condition described. However, there is some creep deformation that is accumulated. Let's get into the process by which this occurs. As a bit of review, you'll recall from our covering temperature effects, diffusion is the main transport mechanism. Atoms move counter to vacancies, driven by concentration gradients, and the formation of new vacancies as temperatures increase. Furthermore, if you recall, one of our barriers to dislocations are interstitial or substitutional atoms, which can reside at the core of dislocations, as I've demonstrated here for an edge dislocation. As diffusion rates start to exponentially increase with temperature, barriers to dislocations also start to diminish. Reviewing the strengthening mechanisms in metals and thinking about how elevated temperatures can affect them, it can be recognized that recovery processes can take place and therefore strain hardening and precipitation is affected because the precipitates age further and coarsen. Phase stability is usually unaffected by creep conditions, unless entering a tempering regime. Grain boundary and solid solution strengthening are affected, but this is less clear as to why. Well, at elevated temperatures, the additional vacancies being added start to allow new directions for dislocations to move. Here I'm showing an edge dislocation that is effectively pinned from moving in the standard way by a substitutional alloying atom. At room temperature, this dislocation could not move, regardless of there being a vacancy nearby. At elevated temperatures, the vacancy, or an atom, depending on how you look at it, is free to move to the immediacy of the pinning atom. The result is that this will enable the dislocation to climb away from the solid solution atom. The result of which is that the dislocation now requires less shear to move, as it is free of the effects of the pinning atom. Now imagine this going on a few trillion times, and we have a complete picture as to how large-scale deformation can occur at temperature with relatively low loads. The role of vacancies either moving or being generated at higher temperatures also explains why grain boundary strengthening diminishes at elevated temperatures for polycrystalline materials. These are naturally spots which contain a large number of vacancies due to the misorientation in the originating solidification event. Therefore, materials which contain a large number of grain boundaries will be particularly susceptible to creep. And this also explains the behavior of the long wire versus the short wire demonstrated earlier. On a cross-sectional basis, both wires will have roughly the same number of grain boundaries, but over their lengths, there are significantly more grain boundaries on one versus the other. So, to review, creep is a time-dependent deformation of a material, and it may occur under static loads which are well below the yield stress. We have looked at how creep is aggravated by both increased temperatures and stresses. The secondary creep regime is where the minimum creep rate occurs. Creep is generally only of concern when the material temperature is above 0.4 of the melting point temperature, or 40%, as dislocation climb relies on diffusion and the presence of vacancies in the lattice. Atoms at the core of a dislocation can move to nearby vacant sites, which effectively allows the dislocation to move by climb. In this way, dislocations can free themselves from a pinning obstacle, move under the influence of the applied stress. Dislocation climb can only occur if there are enough vacancies in the lattice. During creep, dislocations go through a continuous process of climbing, gliding, becoming pinned again, and then climbing free. The dislocation climb process relies on substitutional diffusion in order to free dislocations from obstacles. The higher number of vacancies occurring at grain boundaries explains why fine-grained materials are more susceptible to creep. That about covers it for creep at this stage, and it is a very important aspect of material science, as it does limit a large number of thermal conversion applications. The higher the temperature you can operate a material, the better efficiencies you can obtain over longer periods of time. Until next time.